Hello students, this is Anmol Jain from IT department of AKGEC Engineering College. Today I am going to discuss two important topics of computer organization and architecture that are generally asked in the university question paper. One is the CLA, that is the carry look ahead adder, and another is the Booth's algorithm. So important topics are the carry look ahead adder and the Booth's algorithm for the multiplication. First we will see the carry look ahead adder. So the carry look ahead adder, the purpose of the carry look ahead adder is to replace the ripple carry adder. So what is the meaning of the ripple carry adder is that suppose we are adding two numbers, and while adding two numbers a carry is generated, right, and this carry is forward to another digits, right. So this is done by the ripple carry adder. For the ripple carry adder we use full adder. Suppose we are adding two numbers of 4 bits, then we require the 4 full adder, right. So it adds bit by bit, that is the A0, V0, and it generates sum and a carry, right. So the carry is forward to the next full adder, that is the purpose of the ripple carry adder. That means the objective of the ripple carry adder is to adding 2 bits and forward the carry to the next bit, right. So it takes time to propagate the carry from one bit addition to next bit addition, right. So this is also known as the propagation, carry propagation. So this is the drawback of the carry propagation or the ripple carry adder, is that it takes time to forward the carry, right. So just to reduce this time complexity of the addition, we move forward, that is the carry look ahead adder. So just to understand the carry look ahead adder, first we understand the concept of the full adder. The purpose of the full adder is that it adds 3 bits, 2 bits A, B and C in, that is 2 bits, 1 is carry. So we can complete this truth table of the full adder just by adding two numbers, that is the 0, 0, 0 plus 0, 0, 0 plus 0, 0, the sum is 0, sum is 0 and carry is 0, right. Similarly, when we add these two numbers, 0 plus 0, sum is 0, 0 plus 1, sum is 1 and carry is 0. So in this series we can complete this truth table with the sum and carry. Today we are our objective is to understand the meaning of the carry out, that what the carry out says if we are adding 3 numbers, right. So the logic equation for C0 for the full adder. So the carry for the full adder is AB plus BC in plus AC in, that is these are the 3 inputs A, B and C in. If we found the logical equation for the C out with the help of K map, we find this equation C0 equals to AB plus BC in plus AC in. So we can reduce or this equation to in this form, that the C0 equals to AB plus A plus B and C in is common, right. So this means that we can write our prediction of a carry out bit equation. That means we can predict the carry out operation with the help of the C in only, right. So this can be generalized. This can be generalized in this way, that the Ci plus 1 equals to Ai into Bi plus Ai plus Bi into Ci. So here we find two terms, one is the Ai Bi and second is Ai plus Bi, right. So Ai Bi is known as the carry generator, that we used to write Gi, Ai into Bi, that we call as the carry generator, and Ai plus Bi, that is known as the Pi, that we call as the carry propagator. So these terms to be memorized, that is to be remembered, that what is the carry generator and what is the carry propagator. So generator is the product of 2 bits Ai into Bi, and propagator is the plus of Ai plus Bi, right. So in this way we can find, or we can rewrite the equation Ci plus 1 equals to Gi plus Pi into Ci, where Gi is Ai Bi and Pi equals to Ai plus Bi. So this equation is the number 1, that is the that we will use for the generation of the carry propagation. That means we can find the carry of any number of bit at a given time. Let us see that how we can derive the different carry out operations. So first is C1 equals to A0 V0 plus A0 plus B0 into C0. So that can be derived from the general equation. General equation is, that is Ci plus 1 equals to Ai into Bi plus Ai plus Bi into Ci. So if we put I equals to 1, I equals to 0, I equals to 0, or C1 equals I equals to 0, I equals to 0, then we can find I equals to 0, that is C1 equals to A0 B0 plus A0 plus B0 into C0, right. So in this way we can compute the C1. We can also derive the logic diagram for this carry operation. That is, we are having 3 inputs A0, B0 and Cin. Then A0, B0 we produce the AB with the help of the AND diagram, AND gate, and A0 plus B0 with the help of OR diagram. Then again we use the OR gate just to adding these two components, right. So in this way we can compute the diagram of the C1 carry, right. Next we can move to the logical equation for the C2. So how we can get the C2? Again from the general equation, C2 equals to G1 plus P1 into C1. What is G1? That is the carry generator, right, and P1 is the carry propagator. So just put the value of G1 and P1, right. So what is the value of P1? So we can find the value of P1 from here, that is A1 plus B1. So just put the value of C1 here, just put the value of C1 here, right, which we have derived from the previous equation, that is the C1 equals to A0 B0 plus A0 B0, A0 plus B0 into C0. So just put the value of C1 here and derive the equation for C2. C2 equals to G1 plus P1 into G0 P0 C0 and multiply of P1, that gives the P1 G0 plus P1 P0 C0. Now C2 equals to what? G1 key, just put the place the value of G1, that is equals to A1 plus B1, and put the value of P1, that is A1 plus B1, G0 is, that is A0 B0, P1 A1 plus B1, P0 A0 plus B0 and C0. So what we see here, that the carry 2 is dependent only on the value of the C0 and the given input, right. So this is the importance of the carry look ahead adder, that we can find the carry out at any stage only with the help of the initial carry 0, right. Similarly, this is the diagram for the logic diagram for the C2 that we can derive or we can implement with the help of this logical equation. Next we move to the logic equation of C3. Again write the C3 equals to G2 plus P2 C2 with the help of the general equation and put the value of C2 here. Put the value of C2 here, then put the value of C0 and derive the equation for the C3 just simply by multiplication and addition, right. So we find this again a long equation, but what we see here, that C3 is dependent only on C0. So this is the importance of the carry look ahead adder. That's why I am saying this is a look ahead adder, that it can look ahead the carry. Similarly, this is the logic diagram for the C3. We can derive this logic diagram with the help of this equation for the C3. Next, we move to the logic diagram for logic equation for the C4. Now, what will be the equation for the C4? That is C4 equals to G3 plus P3 into C3. Put the value of C3, then put the value of C0 and compute the complete equation. So, just by putting the value of the previous carry, we can compute the next carry. Again, what we see here, that the C4 is having dependency on the C0, right. So, purpose is solved, that the carry is dependent only on the initial carry C0 and the given inputs, right. So, this is the importance of the carry look ahead adder. This is the diagram for the C4 that can be derived from this equation. That may be complex, but it can be designed. And after completing all the C1, C2, C3, C4 equations, we can design this logical diagram for the CLA, right. That is complex, but we can design it. Similarly, next equation for the sum operation for the adders, that is the same as the full adder. This is the same as the full adder. That is S0 equals to A0 XOR B0 plus XOR C0. That is S0 equals to A XOR B XOR C. Similarly, S1 equals to A1 XOR B1 XOR C1. Similarly, S2 equals to A2 XOR B2 XOR C2. S3 equals to A3 XOR B3 XOR C3. So, we can find out the logic equation for sum as well as for the carry. So, this is for the carry look ahead diagram. So, this is generally asked in the question paper, just how can you derive the equation for the C3 for the carry look ahead adder, or what is the expression for the sum for the S2 or S3 or whatever be the number. So, for just brief, just revise this, you need to memorize these two general equation, number 1 and number 2, and just after putting the value of C0, we can derive the any C1, C2, C3, C4. Next, we move to the important topic that is always asked in the question paper, that is the Booth's algorithm. By using the Booth's algorithm, we multiply two numbers. We multiply two numbers, right. So, just to understand the Booth's algorithm, first we should know, or we will use two operation, that is the sign 2's complement, and second is the arithmetic shift right operation, that is arithmetic shift right operation. Alright, and what is the sign 2's complement? So, first we understand the sign 2's complement. Sign 2's complement is basically used to represent the negative numbers, right, complement, right. So, objective is that we will represent the negative numbers in sign 2's complement form. That is an important. Suppose we are having a number 15 and I say that represent it into sign 2's complement form. So, first is convert it into binary number, simple as we do, that is the 1 1 1 1, put a sign bit separate. This is my sign bit. Now, this is the sign representation of the plus 15, right. Now, suppose I say that represent minus 15 in sign 2's complement, then how I do convert this plus 15 into minus 15 by using sign 2's complement. So, what I do, because it is frequently used sign 2's complement, so the algorithm says that we do not change the value of the plus 15 till the first one. till the first one, as we get the first one. So the first one will be remain till the first one remain unchanged, and after that complement the bits 0, 0, 0, including sign bit, that is 1. So this is the plus 15 representation, and this is the minus 15 representation. So that is important, right? Suppose I am having another number that is having 0, 1, 0, 1 and 0, right? Like, and I say that find its sine 2's complement. Then the sine 2's complement says that from the right hand side move till we get the first one. We do not change the bit value till the first one. First one तक कोई value हम change नहीं करते हैं. That means 0 will be 0, 1 will be 1. After that, after the first one, complement the bits, that is 1, 1 becomes 0 and 0 becomes 1. So this is the sine 2's complement of this number, right? So you should understand these importance of the sine 2's complement just when we are working with the negative numbers, right? Second is the arithmetic shift right operation. What is the importance of the arithmetic shift right operation is arithmetic shift right operation. This says that shift the bit to the right. How? Take an example. For example, we are having bit sequence and I say that make an arithmetic shift right operation. So make a arithmetic shift right operation says that the leftmost bit comes as it is and it is also forward to the right by 1 space or the 1 position. So this is an important, that the 0 is at the same position as well as it is shifted to the next position, and after that this 0 will be shifted to this one will be shifted to this one, and this 1 will be shifted to this 0, and this 0 will be shifted to this 0, and this 1 will be discarded. So this 1 will be lost, and after the ASHR operation my bit sequence will be like this. So these two operations will be used in the sine 2's complement, right? Now next we move to the Booth's algorithm. So Booth's algorithm for the multiplication says before starting the process we do the certain preparation for the Booth's algorithm. That is, number 1, we initialize the accumulator with the 0. AC equals to accumulator Qn plus 1. We will see that what is the Qn plus 1, that should be initialized with the 0, and the SC, that is the sequence counter, that is equals to n, right? Number then BR contains the multiplicand and QR is having the multiplier. BR is a register that will contain the value of the multiplicand and QR is a register that will hold the value of the multiplier, right? So whenever we multiply two numbers, we have a multiplicand and one we have a multiplier. Suppose we are having number 15 and 13 multiply, then this is my multiplier and this is my multiplicand, right? So first step is initialize the accumulator with 0, Qn plus 1, it should be initialized with 0, put a sequence counter equals to n, multiplicand will be held by BR register and multiplier will be held by QR register. Now we compare the last bit of the QR, that is the multiplier, that is we call as a Qn, and this Qn plus 1. So the overall algorithm moves around the pair of this Qn and Qn plus 1, right? So the pair of the Qn and Qn plus 1 will decide that what operation is to be executed. So there may be the following possibilities, that the Qn and Qn plus 1 may be equals to 0 and 1, Qn and Qn plus 1 may be equals to 1 0, sorry, 1 0. That means both bits are different. If both bits are different, then we have to take decision. Qn and Qn plus 1 equals to 0 1. Then what we do, that the accumulator is added with the contents of the Br. That is, the accumulator equals to accumulator plus Br, right. Second, if Qn Qn plus 1 equals to 1 comma 0, if it is 1 0, then accumulator equals to accumulator minus Br, that is, accumulator equals to accumulator minus Br, or we can say the Br complement plus 1, the same thing is. Next, if Qn Qn plus 1 pair is the same bit, if it is 0 0 or it is 1 1, both bits are same. If it is, then we move the arithmetic shift right operation of AC and QR, right. But if we are having Qn and Qn plus 1 equals to 0 1, then accumulator equal to accumulator plus Br followed by the arithmetic shift right operation of AC and QR. Similarly, if Qn and Qn plus 1 equals to 1 0, we perform the AC equals to AC minus Br followed by arithmetic shift right operation of AC and QR, and at the same time a sequence counter is decremented by 1, right. Then we decide the operation on the value of the sequence counter. A decision box is there, that is, if sequence counter becomes 0, that means multiplication is finished, all the bits of the multiplier has been finished, right. If it is not 0, if sequence counter is not 0, then again we move to the pair of Qn and Qn plus 1, right. So just we will understand with the help of an example. Suppose we are having two numbers plus 15 and plus 13 using Booth's algorithm. So just to prepare the multiplication with the Booth's algorithm, first what we do, first we compute the value of plus 15 and plus 13 in binary form or the signed form. So plus 15, that is 0 all ones, and plus 13 equals to 0 8 4 0 1. So this is the signed representation of these two numbers. Plus 15 equals to 0 followed by 4 ones, and plus 13 equals to 0 double 1 0 1, right. Now come to the flow chart. So in the flow chart, what we see, accumulator should be initialized with 0. So this is my accumulator, I will initialize it with 0, and accumulator should have the same number of bits as we have the number of bits in our multiplicand or multiplier. So this is having 5 bits, I have initialized the accumulator with the 5 bits, and it initialized with 0. Second, Qn plus 1 equals to 0, Qn plus 1 should be initialized with 0, right. Sequence, next sequence counter is the n, sequence counter is n, n means number of bits in multiplier. So how many number of bits are in multiplier? That is 1 2 3 4 5, 5 is here, so sequence counter is 5. Next, multiplicand should be held by Br. So multiplicand is plus 15, so it will be held by Br, that is 0 followed by 4 ones, and Qr equals to 0 double 1 0 1. So first step is complete, just to prepare the table of the Booth's algorithm, right. Next, we move to the value of the Qn and Qn plus 1. Let's find the value of Qn and Qn plus 1. So this is the QR register, that's why I am calling it as this bit as Qn, and this is Qn plus 1. So the whole decision will be taken on the value of the pair of Qn and Qn plus 1. So this is 1 0, the value of Qn is 1 and Qn plus 1 is 0. So what the algorithm says, if Qn and Qn plus 1 is 1 0, Qn plus 1 equals to 1 0, then AC equals to AC minus BR. So AC equals to AC minus BR. What I will see here, that Qn plus 1 equals to 1 1 0. Then operation will be what? I make a one column here also. What will be the operation? So operation will be AC equals to AC minus BR, right? So this is my AC and BR. What is my BR? That is the multiplicand. So now I have to compute the value of minus 15. So just by using the sin 2's complement operation, I will compute the value of minus 15. So minus 15 will be 1 as it is, and subsequent one will be complemented, that is 0 0 0 1. So what I have done? I have done AC minus BR, because I have taken the complement of BR, that is the multiplicand, and add these two number, that is 0 plus 1 1, 0 plus 0 0, 0 plus 0 0, 0 plus 0 0, 0 plus 1 1, right? Then what the algorithm says? Performing the operation, perform the arithmetic shift right operation. So how we will perform the arithmetic shift right operation? I will put here arithmetic shift right operation, and the arithmetic shift right operation says that the leftmost bit will be the same and it will be shifted to one position ahead, that is 1, it will be shifted this here also. So generally students get mistake at this point. So followed by this 0 will be here, this 0 will be here, this 0 will be here, and this 1 will be here, and this 0 will be here, this 1 will be here, this 1 will be here, and this 0 will be here, and this 1 will be shifted to Qn plus 1, and sequence counter should be decremented by 1. So this is my first cycle. Right? Next, now again, if the sequence counter value equals to 0, no, this is not equals to 0. If it is not equals to 0, then again move to the value of pair of Qn and Qn plus 1, that is a 0 and 1. Put it here 0 and 1, and what the 0 1 says as per algorithm, if it is 0 1, then accumulator equals to accumulators plus BR. So accumulator is here and BR is there. Put here 0 followed by 4 1s, that is AC equals to AC plus BR. Add these two numbers, that is the accumulator equals to accumulator plus BR, that is 0 plus 1 1 1 1, 1 plus 1 0, 1 carry, 1 plus 1 0, 0 plus 0 0. The carry will be discarded here, right? Then perform the arithmetic shift right operation. Arithmetic shift right operation contains of the AC and QR. Remember it, AC and QR both will be shifted as per the ASHR operation. So ASHR says this 0 will be here and this 0 will be almost will be shifted to one position ahead, and followed by 0 triple 1 1 0 double 1 0. So this is my second cycle is completed, and sequence counter will be decremented by 1, that it becomes 3. Now what is the value of sequence counter? Again this is not equals to 0. So again put the pair of Qn and Qn plus 1, that is 1 0, and 1 0 says AC equals to AC minus BR. So AC equals to AC minus BR. So again the AC equals to AC minus BR, that we have to take complement of minus BR, that is plus 15, that is 1 followed by 0 0 0 1. Add these two number, 1 plus 1 0, 1 carry, 1 plus 1 0, 0 plus 0 0, 1 carry, 1 plus 0 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 1. Then perform the arithmetic shift right operation, right. Arithmetic shift right operation says this 1 will be here, this 1 will be here, 0, 1, 0, 0, 1, 1, 0, 1, 1. So this 1 will be shifted here, right. Now sequence counter will be decremented by 1, again becomes 2. So I have completed 3 cycles, right. Now what is the value of the sequence counter? This is equals to 2, but it is not equals to 0. If it is not equals to 0, then see the pair of Qn and Qn plus 1, that is 1 1. So what the 1 1 says now, if Qn and Qn plus 1 is the same bit, that is 1 1, then there is no need of the plus operation or the minus operation. Just simply put the arithmetic shift right operation, right. So just I will make an arithmetic shift right operation here, arithmetic shift right AC and QR, right. So put the arithmetic shift right operation. Arithmetic shift right operation says this one will be here and it will be shifted to right position also, that is 1 1 0 1 0 0 1 1 0 1, and sequence counter becomes 1. Again what I see that the sequence counter is not equals to 0, so we will move ahead, right. We will move ahead means again we will check the value of Qn and Qn plus 1. So the value of Qn plus 1 is 0 and 1. If it is 0 and 1, then what operation will be performed? That is the AC equals to AC plus BR. So what is my BR? That is 0 4 times 1, 0 4 times 1. Add these two number, 1 plus 1 0, 1 carry, 1 plus 0 1, 1 plus 1 0, 1 carry, 1 plus 1 0, 0 plus 1 1, 1 carry, 1 plus 1 0, 0 plus 1 1, 1 carry, 1 plus 1 0 and 0 plus 0 0, and carry will be discarded and followed by arithmetic shift right operation, right. Arithmetic shift right operation says 0 as it is, 0 will be shifted here, 1 1 0 0 0 0 1 1, and this 0, and this will be decremented by 0. So now what I see that the value of the sequence counter has become 0. So now stop the process. Important thing is the result is stored in AC and QR of register. So this is my result, right. This is my result. Result is stored in AC and QR. So if you change the value of AC and QR, you will find the value of the product. Value of the product is that is 00110, right. If I convert it into decimal, then it will be equals to that is 1 2 4 8 16 32 64 then 128. If I add these two numbers, add these numbers, 1 plus 2 3 plus 4 7 plus 8 15, 1 carry, 7 plus 2 9 195. So if you multiply the 15 into 13, we will find the same number decimal, right. So you can check it whether you have done the correct or not, right. I can do it very simply that sometime it is asked that how many addition operations, how many subtraction operations are performed in a given multiplication. So I can have a quick review for this. Suppose I am having plus 15 into plus 13. So these operations these operations are independent of this number. Just you convert this number into signed representation, that is 0 1 0 11 0 1, and put a additional 0 as we do in this qn plus 1 operation. Then simply apply the Booth's encoding. Booth encoding says that make a pair of this 1 0, then 1 0, overlap it 0 1 1 0 1 1 and 0 1, and just put the Booth's encoding. 1 0, that is the subtraction, 0 1 addition, 1 0 subtraction, 1 1 arithmetic shift right, 0 1 addition, and ASHR will be performed after each operation. ASHR will be performed. So we can find easily that how many addition and subtraction will be performed. So subtraction 1 2, so subtraction equals to 2, addition equals to 1 2 2 addition, and arithmetic shift right operation, that is 1 2 3 4 5. So you can easily answer these number of operations performed during a Booth's algorithm. I hope that you will learn this topic easily with the help of this video, and you can answer these questions in competitive exams very easily and very quickly or within a seconds. Thank you.